Okay, so we're going to continue our work with scatter plots and bivariate data. We're going to look at actually putting a line to a scatter plot. And what we're looking at is a line of best fit. It's not going to be perfect. It's going to be a line that approximates the trend of that data. And what I draw as a line of best fit might be different than what somebody else draws for a line of best fit. But they should do a decent job of going through the middle of our data, and middle is a very arbitrary idea. But one thing we can do to help get a little bit closer is go through a common point. One thing that will help us narrow down where a line should go is by using the mean point for our scatter plot, and that mean point is going to be the average of the x's, comma, the average of the y's. So here we have some data, and we're going to find the mean number of grams of fat. So that's our mean, that's our x bar. Find the mean number of calories, that's our y bar. And we're going to make a scatter plot and plot the mean point on our curve or on our graph, and then use that point to draw a line of best fit. So first we calculate the mean of each column. I think we can do that by this point of the game. Mean grams of fat, 22.45. Mean number of calories, 457.27. And then for our scatter plot and point with line of best fit, it should look something along the lines of this. Labeling our mean point, and the line goes through that point. And ideally we want it to go through one of the other data points if possible also, for ease of writing an equation that fits our data. And we'll do that in the next example. So what we're looking at is a regression line. It's the equation for the line of best fit. This is why we want our line of best fit to ideally go through one of the other data points, but it doesn't have to. And we're going to use this regression line to help us make predictions for other data values that might not have been collected. So here we have a class of 10 students for their classwork and their final exam score. Caroline, if you notice, she was absent for the final, so we don't have a pair of data here for her. What we're going to do is simply omit her from our data analysis. We can't use it. We don't have a score. We need to find the mean classwork, the mean final exam score. We're going to make a scatter plot and draw a line of best fit going through that mean point. Then we're going to find the equation of our regression line and use that equation to see if we can't predict Caroline's exam score. So she scored an 80. If she fits the trend with the rest of the class, what is her score going to be approximately? When we use our line of best fit, and that's what we're going to do for E, when we use the line of best fit to predict a data value within the range of the given data, it's called interpolation. It's more reliable than extrapolation, which is where we go outside of the values that we have and make a prediction for something way different than the data we were looking at. Extrapolation is not very good because we have no way to know if the data trend is going to continue. We're fairly confident that within these scores, there is a trend. And using that trend to predict new values, that's what we're calling interpolation. That's not a bad thing. So, find the mean classwork, mean final exam, construct a scatter diagram, draw a line of best fit. Here's what we're going to do. I'm going to jump over to the calculator, and we're going to look at how we can do this. So, I have put in my X and Y data, my classwork, and my final exam score. Question would be, does classwork influence the final exam? The final exam is our dependent variable. We're thinking it depends on how much classwork was done. So we need to find the mean of these things. So here's what I'm going to do. I'm going to call this, I'm going to add a calculator page. And I'm going to type X bar. And I'm going to press Control, and then this colon equal sign here, that I'm going to define X bar to be mean of my class column. So X bar is now stored to be 75. And I'm going to call Y bar, and this is the defining equals. I'm defining that to be the mean of my final. Notice it bolds it because final is a variable that I have stored. It's a list on slide 1.1. So 75, 72. I'm going to make a scatter plot now, and I want this average point, this mean point, to be plotted. So I'm going to go back to 1.1. I'm going to go down to the bottom of my list, and I'm going to plot a 10th point. I'm going to put equals X bar. Just added 75 as my X coordinate. Equals Y bar. It added 72. So now when I make my scatter plot, that point is going to be included in addition to the rest of these. So control, add a page. We're going to add data and statistics. I'm going to have my classwork be my independent variable. My final exam score be my dependent variable. And you notice there is moderate positive correlation here. And hovering my hand over, you can see that this is my average point. It's my X bar, Y bar point. So now we need to do, we've got our scatter diagram. We need to draw a line of best fit. So this is something you're doing on your paper when it asks you to draw this. You should create this picture. So I'm going to, on my paper's electronic, of course, I'm going to draw a line that goes through that point, or roughly through that point, and I'm going to hope that it goes through one of my other points also, just to make writing an equation a little bit easier. So that line does a decent job of having some points above it, some points below it. It's sort of going right down the middle of my data. So when I write my equation for this line, I can use that point, my mean point, and this point. It's an approximation of where this line is going. So let me go back to my graph. That is 95, 95. So now we have to remember our algebra skills. We're using the points 95, 95 and 75, 72 as 2 points that our line goes through. So how do we write the equation? Well, we need a slope. We use m to abbreviate it. Change of y over change of x. So 95 minus 72 over 95 minus 75. So this slope would be 23 over 20. That doesn't reduce. I'm just going to leave it as 23 over 20. Now, how do we write this equation? Well, we have a point slope form, y minus y1 equals m times x minus x1. And x1 and y1 are a point on the line, and the point on the line that I want to use is actually my y bar and my x bar, my average point. This x and this y stay x and y. So my equation becomes y minus 72 equals 23 over 20 times x minus 75. And I could, if I wanted to put this in slope-intercept form, we simply have to distribute the slope and then get y by itself. But this is an equation for the regression line that I drew. Now we're going to use this equation to estimate Caroline's score for the final exam. Well, how do we do that, guys? Well, we plug in x equals 80. So y, her exam score, equals 23 over 20 times 80 minus 75, and I'm adding the 72 onto this side, and we can take a calculator and easily find out And when I do this, I get a score of 77.75. So we should expect that based on Caroline's classwork, she would score approximately 78 on the final. Next two examples, last two examples, are looking at, do you understand what these regression equations mean? So we have a study investigating the relationship between age and the time in minutes the child can run 1 kilometer. So we collected data between the ages of 7 and 18, and we came up with this equation for our regression line. What does slope and y-intercept mean? Well, slope is negative 1/2. We have to look at units here. It's the time in minutes and age in years. So if we think about slope being change of y over change in x, we're talking how much the y changes, how many minutes, versus compared to how the years change. So we're going down half a minute per 1 year. So the time decreases by half minute per year. Or you could interpret it as being that the time decreases 1 minute every 2 years. We know it's negative on the slope, so the time has to be going down. What does the 20 mean? That's the y-intercept. That would be the time it takes for a child who is 0 years old. That's what y-intercept is. That's the value for y when the input is 0. Well, in this case, that doesn't make any sense because we can't have a 0-year-old running a kilometer. It simply can't work. But hypothetically, this would be the amount of time it takes for somebody to run if they are 0 years old. Physically, that doesn't make sense. And that's what this note over here asks you to always think about when you're doing these sorts of problems. And lastly, we have a biologist studying the relationship between the number of trees, x, per hectare, pronounced that wrong, and the number of birds, y, per hectare. She calculates the equation of the regression line to be 8 plus 5.4x. State the gradient, aka slope, and the y-intercept and interpret them. Okay, so slope is 5.4. Change of y over change in x. You can always think of the slope as being over 1. So if for every 1 hectare increase in trees, we see 5.4 increase in birds. Y-intercept would be the number of birds if we have 0 trees per hectare. So there are 8 birds when there are 0 trees per hectare. Now think about this. We're probably someplace that has trees. Is this necessarily going to work? Do you think this value, that getting 8 when there are 0 trees per hectare, do you think this is extrapolation or interpolation. And this would probably be interpolation unless we knew this would probably be extrapolation unless we knew that we took a measurement at some place that had 0 trees whatsoever, and we found that there were 8 birds per hectare. So that is where we stopped. We talked about how to compute the regression equation by hand, and also how to interpret these regression equations. In the next sections, we're going to look at how we do this using technology and coming up with the best line of best fit.